Swayam Prabha. Digital India. Educated India.
Welcome to today class of nonlinear vibration. So, in this module we are discussing regarding several applications of nonlinear vibration. So, initial classes we have studied regarding the application as a energy harvester, then we have studied the passive and active vibration observer. So, last class we have studied regarding the application of this nonlinear vibration in case of the tuning problem, and today we will consider two more applications. So, for example, so in case of the cold rolling mill and then artificial muscle. So, let us see what is the charter in case of the cold rolling mill. So, we will study the charter in rolling mills. So, need to study this charter in rolling mill you should know. So, during cold rolling of sheets, undesirable mechanical vibrations get produced, which generally referred as chatter. So, chatter becomes more dominant as rolling speed increases and can lead to unacceptable gauge variations, sheet corrugations, then surface imperfections, damage to mill and unacceptable noise in work environment which affects the product quality. So, to improve the product quality you must see that what are the parameters affecting this chatter in the rolling mill, and we have to avoid this chatter, and how to avoid this chatter is also this concern. So, which we can study through this dynamics. So, there are different type of chatter regimes in the cold rolling mill. So, there are three different types of chatter occur in rolling mill characterized by their frequency range or musical octave of natural frequency associated with the dynamic mechanism involved. So, one is the torsional chatter which generally occur from this 5 to 15 hertz frequency. Then third octave chatter, so this is 120 to 240 hertz frequency. Then fifth octave chatter which you can see from 550 to 650 hertz frequency. So, generally these three types of chatter occur in this rolling mill. So, due to gauge variations, third and fifth octave believed to be responsible for most damage to the products. So, we have to avoid these third and fifth octave by operating the system away from this frequency, or we have to develop some means so that we can avoid this chatter in this field. So, there are several pioneer works in this field. I will show you the literature. So, particularly this by Roberts, so who has considered the fifth octave chatter, then by Chepnock et al. So, they have considered the 4 degree of freedom chatter model of a 4 high rolling mill. So, there are several rolling mills available. So, the simplest kind of rolling mill considered in dynamics is the 4 high rolling mill, and so they have considered self excitation. They have shown that chatter is a self excitation phenomena, tends to occur when there is sudden change in the rolling force. So, they have shown that there is due to the sudden change in the rolling force. So, chatter occur in the system. So, this is a self excited vibration. Similarly, this Johnson and Quick developed a 2D and 4 degrees of freedom model to examine the chatter phenomena. 2 degrees of freedom model consists of a squeezing model, squeezing mode and motion of the mass center to represent the frequency of fifth octave chatter. So, slightly higher because of sheet deformation force and also unsteady interstrand tension can induce instability if sufficient damping is not available. So, nonlinearity and its effects are also explored in this work by this Johnson and Cui. Similarly, Yoon et al. So, they did a series of work. So, they did the review of different modes models proposed on rolling chatter in the literature, so as to get better understanding of the chatter. Correlation between different rolling parameters been proposed in 4 to 6 by the same author Yoon et al. So, in dynamic rolling model, they estimated variations in the exit gauge, strip speed, tension at the entry and exit, rolling force and rolling torque in response to the variation in rolling separation, as well as the rate of change of roll spacing. So, results validated using experiments and sources of chatter also recognized in this work. So, with a chatter model, they try to understand the conditions which leads to the dynamic instability, and they proposed that negative damping, mode coupling and regeneration are the basic mechanism which lead to chatter in rolling. So, they have shown that negative damping. So, already we know how to analyze a system with negative damping, then mode coupling and this regeneration they thought are the basics of the chatter produced in the rolling mill. So, they are the coupled dynamic rolling model with unimodal chatter model and simulated the results to show roll force, roll gap, back tension variation leads or lags in phase to produce negative damping. In mode coupling, they took roll vibration in more than one direction and attempted to show this as one of the cause of chatter. So, then there are some other work also pioneer work by these Eman et al. So, they continued their work and a dynamic rolling model considering homogeneous material also presented, and here roll movement in both directions has been considered. Experimental results found in agreement with the simulation results using established linearization form. Eman et al. Continued their work and produced another dynamic model considering non-homogeneous material also. So, this Eman, so they have considered both homogeneous and non-homogeneous material. So, these are very good work you can study in case of the rolling. So, there are several other work also available. For example, this Wikio Kumara et al. Work is there, and some other work by this Mihan and Rogers. So, several other works are available which you can see in this Lin et al. Also. So, he has this work on this instability in case of rolling mill. So, also you can see some of our work related to rolling mill, particularly by Sajan Kapil and Eberhard. So, let us see this mathematical modeling. This work is by Shailesh Dhutekar, who was the MTech student, was my MTech student. So, he did this work. So, the mathematical model has been created in a view to study the characteristic of fifth octave chatter. In this case, it consists of two parts, namely work roll submodel. So, the total analysis is divided into two parts. So, one is this work roll submodel and the second one is the roll byte submodel. So, combining these two model, the rolling mill model has been developed, and it is then simulated to find the response in case of this milling in case of this rolling operation. So, this is a 4 high rolling mill. So, 4 rolls you can find 4 rolls. So, here 4 rolls. So, the upper one are known as the backup roll. So, this is the backup roll and the side also the backup roll. Then we have a work roll. So, these two are the work roll which press the this ingot to make it in seed form. So, then you just see they are rotating in opposite direction, and while this is rotating in clockwise direction, the other one is rotating in anti-clockwise direction. So, due to as both of them are rotating in opposite direction, so the strip enters here and it get pressed and you can get a seat. So, this model can be represented. So, this work roll model can be represented. So, this is the seat, the seat will provide a force, seat force Fs. So, it will press this work roll, or in turn this work roll place this seat, and the force between this back of roll and work roll can be modeled as a spring. So, you can model this as a linear spring or nonlinear spring. So, here it is model F equal to minus K y. So, y is the displacement of the work roll. So, then this force is written as F equal to minus K y. So, this way you can write down this work roll submodel. So, in work roll submodel, a 4 high rolling mill stand configuration is considered for the formulation. The assumption is that the physical association between the work roll and the back of roll can be modeled as spring, and the damping between them is negligible. So, as there is point contact, so this damping is considered to be negligible. So, there is no separation between the work roll and the back of roll at all times when the mill is running. So, they are in contact. So, there is no separation between them. So, that is also the assumption. So, now you have seen we can write the equation of motion of this upper work roll like this: m d square y by dt square plus k y equal to Fs. You have seen the free body diagram. Here from the free body diagram, so you can write the equation of motion. So, this is m, work roll mass is m. So, as the motion is y, so the inertia force is my double dot. So, then this F equal to k y, the spring force or the force exerted by the back up on the roll, and this is the seat force. So, taking all these three forces, so the equation can be written as m d square y by dt square plus k y equal to Fs. So, the spring stiffness actually can be obtained. So, by knowing the force acting between the this work roll and the back of roll. So, this force can be determined experimentally, and this k can be written by this del f by del y. So, one can plot this f versus y, and from del f df by dy one can find the spring stiffness. Now, the displacement of the work roll due to compressive load F per unit length can be given by, so from this work. So, initially we have seen, so y can be written as 2 f 1 minus mu square by pi e into 2 by 3 ln plus 2 by 3 ln. So, 0.78125 E dW plus dB by F into 1 minus mu square. So, you can take that relation from there, and then it can be k can be assuming, so differentiating that thing. So, that is k. So, differentiating that thing, so the expression can be written in this form. Here the stiffness k is nonlinear function of seat. The exerted seat force and the work roll displacement can be decomposed into steady and dynamic part. So, one can it can be, so this force can be divided into two part. One is the steady state part and the constant part and the dynamic part. Similarly, y can be written as the y steady part and the dynamic part. Dynamic part means which is varying with time, and steady is a constant part. The work roll submodel can be represented by m d square y d by dt square. So, as the differentiation of the steady part will leads to 0. So, we can have the dynamic part only we can write for the dynamic motion. So, m d square y by dt square m d square y d. So, this is the dynamic part of the displacement plus k y d equal to f d s. So, the roll gap h c can be written as h c 0 plus 2 y d. So, as we are considering 2 work roll, so that is why. So, this roll gap can be written as h c equal to h c 0, this is the initial gap, plus 2 y d. So, this h c 0, that is h c at t equal to 0 and h c equal to, so at initially then this h c will be equal to 2 y d. So, then we can see the roll bite model. So, in the roll bite models we can consider the stress acting on the sheet. So, the side, for example, let us take this is sigma 2, this is sigma 1. So, due to, so there is a tension. So, in this thing, and u1 is the velocity in this side, it is inlet side, and u2 is the velocity of the strip in the outlet side. So, this is initial gap, roll gap. So, h can be retain this thing. So, this is the h and this is the entry. So, at this entry, so at a distance x 1, and it is, let us consider the radius of the roll equal to r. So, we have taken this direction as the x direction, as this as the y direction. So, we can write. So, figure 2 shows the roll bite of a metal sheet being rolled between two work roll, which follow from the work of Hu and M1. So, metal sheet is homogeneous and ideally elastic plastic, which the Tresca maximum shear stress failure criteria is applicable. So, using that criteria, so the mathematical model has been developed. So, using parabolic approximation of the roll bite. So, the strip thickness within the roll bite as a location x can be written as hx will be equal to hc plus x square by r. So, applying this principle of conservation of material flow volume, the material flow through a vertical cross section at a distance x can be written as u x hx equal to u1 h1 minus x1 minus x into hc. Tresca maximum shear stress criteria for the plane stress condition can be defined. So, tau y square equal to 1 by 4 sigma xx minus sigma yy square plus tau xy square. So, and a friction factor definition can be taken tau s equal to plus minus m into tau y. The simplified criteria for homogeneous deformation can be taken sigma xx minus sigma yy will be equal to 2 tau y. So, taking all these approximation. So, now the distance x 1 measuring from the strip. So, distance x 1 measuring from the strip to center line of the roll is x 1 equal to h 1 minus h 2. So, this is h. So, this is s plus delta h, taking h plus delta h. So, we can find this x 1 equal to h 1 minus h 2 into r root over, and the strip exit position. So, this is the entry position. So, entry position. So, from the previous figure also. So, this is, so from the center line of the roll. So, you can find this distance as the entry and this is the exit. So, it will exit at here, this is entry. So, it is, this is a small strip is shown, entry exit you can see from the previous figure also. So, from this figure, so you can see, so from the center line. So, this is x 2, that is exit. So, it is exit at here. So, it is parabolic. So, we have considered a parabolic strip. So, here it is entry, clearly you can see this part is x 1. So, this is x 1 entry and this is exit. So, at this point we are assuming to be exit, that means after this thing the thickness becomes uniform. So, here this to this the deformation takes place. So, it is pressing to have this deformation here. So, taking a small strip, so we can write down. So, this is sigma x, this side it is sigma x, this side it is sigma x plus d sigma x. So, this height is h plus dh, here the height is h. So, at a distance dx. So, after x we are taking a small strip of distance dx. So, the exit can be written as r h c into h c by 2 into u1 h 1 minus x 1 into h c. So, this, so the roll bite gap at exit position is thus h 2 equal to h c plus, this is the initial gap, h c plus x 2 square by r. The static equilibrium position for the vertical side, so can be obtained from this expression. So, doing this force balance. So, you can do this thing. So, sigma x plus d sigma x. So, this is sigma x plus d sigma x, then this, so multiplied by this area. So, thickness will be same. So, this or width will be same. So, taking that thing sigma x plus d sigma x into h plus dh plus minus 2 tau s root over dx square plus dh square by 4 cos phi plus 2 p root over dx square plus dh square by 4 sin x equal to sigma x into h. So, where cos phi equal to, so you can see, so this is the angle phi. So, with the horizontal, so this is the this line you just see. So, this angle is phi. So, this cos phi equal to dx by root over dx square plus ds square by 4 and sin phi equal to dh by 2 into dx square plus dh square by 4. So, taking this way, so it can be further simplified, this dh by dx into sigma x plus p plus h into dx d sigma x by dx plus minus 2 tau s equal to 0. So, where the sign of friction term determined by the position of x, all the right hand side of the neutral position x n, the friction is positive and on the side other side it is negative. The horizontal stress distribution at arbitrary position x can be written as sigma x equal to sigma 1 plus x 1 to integration x 1 to x 2 tau y by h x minus plus m minus 2 x by r dx. So, sigma x. So, you can write in this form, then considering sigma to location x 2, then x n can be found here, that is x n is the neutral position. So, neutral where it is changing, the sign is changing from negative to positive. So, x n can be found. The roll gap at neutral position h n can be written as x c plus x n square by r. The normal pressure P is given by P x equal to 2 tau y minus sigma 1 plus integration x 1 to x 2 tau y by h x minus plus m minus 2 x by r into dx. So, then the resultant sheet deformation force can be calculated F s. So, from this expression, so you can calculate the this force, resultant sheet deformation force. So, that is due to pressure and due to shear. So, both the things are there. So, due to pressure, so this is P x into dx and then for shear, so this part is there. So, expanding this above equation, so you can get the expression for F s. So, this the purpose of this roll weight model is to find this force F s, this force F s. So, after getting this F s, now we can substitute it in the original equation, that is m d square y by dt square plus k y equal to F s, and simulate that thing. So, we can use this Runge-Kutta method to do that simulation, or you can use the Simulink model, and here it may be noted that several other models can also be developed to find the response. So, initial condition, initial y d equal to taken 1% as h c 0 and y d dot are taken to be 0 for the simulation. So, here in this case of numerical analysis, when the inlet strip thickness is 2.54 mm and the initial position of the upper roll is h c 0 is 1.8 mm. So, friction coefficient are said to be same in both backward and forward direction, that is m 1 equal to m 2 equal to 0.1 is considered. Here the work roll mass is considered to be 2299.98 kg per meter. Strip shear strength of aluminum is 110 MPa. Work roll and backup roll diameters are 0.61 and 1.52 meter respectively. Friction coefficients equal to 0.1 and and the front and back tension are less than 170 MPa, less than yield strength of the strip material. So, this back tension and these front and back tensions are taken to less than the yield stress of the strip material. So, if you can simulate this thing, then this work roll deflection, that is y, can see it is in this form. So, 1.92 into 10 to the power minus 2. So, that means 1.92 mm. So, maximum. So, in the initial position you just see initially, so there is some vibration. So, that is or the and it after some times it settle down. So, but in this case when, so this is the speed is 12.7 meter per second. So, it settles down at 0.01 second, but if the speed is increased to 25.5, so you just see, so this amplitude is also increased and also the settling time is also increased. So, it has a greater settling time, so there will be some chatter mark on the tool. Similarly, it can be the effect of rolling speed and varying friction factor on the mill vibration can also be studied. So, rolling speed is 2.54 meter per second. So, this is, you can see here the work roll deflection is less than this thing 2.54, previously we have taken more, and here we have taken the effect of unequal friction. So, it is taken this M1 M2 0.1 is taken. So, if we are taking this M1 and M2, M1 is 0.1 and M2 equal to 0.7. So, you can see that, so here you just see, so there is initially, so there is no oscillations here, but in this case you can see some oscillation taking place. So, but there is the initial roll gap is there. So, it will cover through this initial roll gap and there then it is smooth, but in this case, so there is a initial deflection in the initial deflection is there. So, which will result in the chatter mark in the sheet, and you can see more chatter mark you can get. So, effect of varying the front and back tension. So, by varying the front and back tension, so you can see lot of oscillations occur, or and due to that thing some marks will be there. And so, if the entry, the inlet thickness at entry at 0.05 second and 0.02 second. So, in this figure, so it can be this some portion has been taken and plotted it here. So, you can see, so there is lot of oscillations in the strip. So, due to these oscillations, so there will be mark on chatter mark on the tool, chatter mark on the strip will be there. So, here you just see, though in previous case we have seen there is less undulation, or quickly it has reached to the that steady state response, but in this case the system response is 0.01 mm strip entry thickness. So, here effect of reduction of strip thickness. So, if we have a very small strip 0.01 mm, so in that case more oscillations will be there, and clearly, so it can be clearly seen that this friction factor model does not give good result for small entry thickness. So, if we have a small entry thickness, so in that case you can see this model is showing that always there will be chatter mark in the strip. So, in this way one can do this analysis of a 4 high rolling mill. So, one can study other different type of rolling mills also. Also one can take this linear stiffness K to be nonlinear, and in that case the analysis will be different. So, there are several other roll bight models are available, and some recent roll bight model studied by Sajan, Kapil and Everhard and myself. So, you can see those things, and these are the references what we have seen in this work. So, the reference is Robert and Johnson, Roberts, E Johnson, Quan Kui. So, this is a old paper 1993. So, Charter Dynamics in Sheet Rolling. So, International Journal of Mechanical Science. So, then you can see this paper, Chefnox and Fishback and Ojou in 1984. So, study and industrial control of chatter in cold rolling. So, Iron and Steel Engineers Journal. So, then Yoon, so he has lot of paper in this field. So, Yoon, Wilson and Ehman. So, 1988 review of chatter studies in cold rolling. Then Yoon, Wilson and Ehman, charter in strip rolling process. So, part 1 and part 2. So, they have 2 parts in this paper. So, dynamic rolling model. So, it is published in this ASME Journal of Manufacturing Science Engineering, and then Yoon, Wilson and Eman, charter in strip rolling process. So, part 2. So, dynamics rolling. So, here experiment has been carried out. So, this is published in ASME Journal of Manufacturing Science Engineering. Yoon has several other paper also, Yoon, Wilson and Eman, 1998, charter in strip rolling process, part 3. So, charter model. So, Eman has several other papers. So, Pei Hua Hu and Eman KF, 1999, a dynamic model of rolling process, part 1 homogeneous model, and in part 2. So, they have this inhomogeneous model studied. Then Kimura, Sodani, Nishihura, Ikeuchi and Mehera. So, in 2002, charter analysis in tandem cold rolling mill. So, there is a tandem means a number of rolling mills are there. So, in tandem rolling mills you can see this work. Then Mehan and Paul. So, vibration instability in rolling mills, modeling and experimental result. So, then Farley and Rogers and Nardini. So, understanding mill vibration phenomena, Innoval technology. So, this is a good paper. So, you can find this paper. So, Lin, Langari, now. So, on characteristics and mechanism of rolling instability and chatter. So, this is also published in ASME Manufacturing Science Engineering. So, in 2003. So, you can find several other papers in rolling mill and some recent papers also in rolling mills are there. So, where you can study the rolling process. So, this way we have studied 2 manufacturing process, and we have one is in turning operation, one is in this rolling operation. Actually, so this turning operation can be extended for milling operation and boring operations also, and this rolling operation can be in forming operation. The basic idea is to, or basic thing is to find a force. So, this force sometimes it is a nonlinear force which is a function of the displacement of the sheet metal. So, in that case it can be modeled as a parametrically excited system, and considering this nonlinearity, so we can have different resonance conditions. For example, we have studied principal parametric resonance conditions, combination resonance conditions, and also in addition to that, in case of simple resonance conditions, we may have superharmonic and subharmonic resonance conditions at different frequencies. So, we can study all these type of vibration depending on the applications and in which range of frequency the system is operating. So, this way we can study the nonlinear vibration of manufacturing systems. So, let us see some more electromechanical systems. For example, so let us analyze now a pneumatic artificial muscle. So, a pneumatic artificial muscle is used generally for actuators. So, pneumatic actuators can find many application. It can find applications in the rehabilitation process also. So, or in these exoskeletons one can use this pneumatic actuator. So, in mechatronic systems either one can use a hydraulic system or pneumatic system. Also one may use these motors. So, electric motors where it may be this DC motor, AC motor. So, also it may be this servo motor, stepper motor. So, depending on the motor and or depending on the these prime movers. So, one can model the one can dynamically model the systems, and after modeling the system one can find the response of the system to study the system. So, always this dynamic model will be very useful to study the dynamics of the system. So, now we are going to study the nonlinear dynamics analysis of pneumatic artificial muscle actuator under force and parametric excitation. So, already we have discussed what is force excitation, particularly we tell about force excitation when the or force vibration of a system. So, when the system is when the direction of the force and the response takes place in the same direction, but when they occur in perpendicular direction, generally we talk regarding the parametrically excited system. So, these are different type of various palms. So, the first one, so you can see this is Mickey vein muscle or braided muscle, then pleated muscle. So, you can see this pleated muscle, then we have palm reinforced with Kevlar fiber, then airload net muscles, then so there are several other muscles are there. So, these are the muscles actually used in several applications. So, here we have to apply this pneumatic force or air we have to introduce into these braided muscles. So, due to the air force, so this will expand in the transverse direction and there will be a contraction in the longitudinal direction. So, due to this contraction or this contraction can be used for actuating this muscle. So, we have to provide this air force or pneumatic force by either using a blower or the compressor, and we can actuate these muscles for different applications. So, this pneumatic artificial muscle. So, actually this work is part of the PhD work of my PhD student. So, now he has defended his thesis. So, he is Dr. Bhaven Kalita. So, this is the part of the work by Dr. Bhavan Kalita, who was my PhD student. So, here this pneumatic artificial muscle is a soft actuator. So, that is compact and lightweight in nature and the characteristics similar to those of the human muscle. So, these actuators are obtained power by air pressure applied into the bladder, which are made of elastic viscoelastic material such as rubber. So, the physics behind the operation of palm is the same with that of human muscle, as it converts pneumatic power into pulling force. So, here in case of the human, so we are, for example, in our hand we use our tricep and bicep to actuate the hand motion. Similarly, here by putting this pneumatic force, so we can achieve this pulling or pushing action. So, the palms are much suitable for various applications like exoskeleton along the rehabilitation assistance, grasping and handling delicate objects with complex geometry, the robotic mechanism where multiple sophisticated movements required, industrial and service robotics also we can use. So, due to the threshold pressure, irregular effect of bladder geometry, the elastic energy of the rubber bladder and the braid of the muscle, a nonlinear characteristics can be observed. Some other parameters like this compressibility of air, material properties, valve actuation and load contraction characteristic due to flexible structure also added nonlinearity to the muscle dynamics. So, these qualities and drawbacks make the palm as an attractive topic for many researchers and industry to study various behavior of the palm in different applications or different environments. To understand the dynamics behavior of palm, different types of models have been presented in literature. So, experimentally generally these material characteristics of the palms are first derived and then this actuation force in terms of different muscle contraction and muscle parameters have been developed by different researchers. So, we will see all those. So, some of the literature are by this Chu and Hanford and Tondu and Lopez. So, mostly used basically virtual work and of an extremely thin inner tube and continuously cylindrical shape artificial muscle. Vikramatunge and Lipak Preda. So, they derived empirical model experimentally to understand the mechanical behavior of farm. Lee et al. Derived experimental model which established a relation between the operating air pressure, muscle force along with the contraction of the palm. So, here in this work we followed this expression of Lee et al. And we have conducted our own experiments also to characterize the palm. So, Ashwin and Ghoshal presented different mathematical models for representing the statistics of palm based energy balance method. So, there are several others researchers worked in this field, and you can find lot of work related to this pneumatic artificial muscle. So, now I am going to show you 2 or 3 models. So, the first model is nonlinear dynamics of harmonically excited palm. So, here I will show you both experimentally and theoretically how this equation of muscle, how this artificial muscle work, and let us see this first model. So, this is here we are going to study the nonlinear dynamics of harmonically excited palm. So, let us consider. So, this is a palm artificial muscle, pneumatic artificial muscle. So, these pneumatic artificial muscles you just see. So, entry and exit. So, you can see. So, it is this from air compressor, this air is going through a control valve. So, from this control valve it is put inside this muscle so that it can contract. So, when it is contracting, so you just see this side we have a spring also and spring and damper. So, the spring and damper. So, initially let us have a spring damper system. So, already you are familiar with a spring damper system. So, now by putting this artificial muscle or this pneumatic actuator, so we have to actuate this muscle force. So, let us apply a force F sin omega t to this system, and our objective is to move this mass by applying this force. So, now the equation of motion can be written. So, here also we have added the inertia force. So, inertia force is shown here. So, the spring force Ku, inertia force mu double dot, and damping force Cu dot, and this muscle force F muscle, and this is the excitation force acting on the muscle, that is F sin omega t. So, here this muscle force actually is characterized by the, so it will be different for different type of muscles depending on the muscle material, depending on the braid of the muscles and different other parameters. So, this F muscle will be different, and it is a function actually of the contraction U and also this pressure P. So, this muscle force can be written U P, F muscle U P can be written as C1 plus C2P plus C2P square into U minus U by L plus K U cube. So, we have written this thing by using a nonlinear term K U cube, and so here that means we have taken 4 parameters, one is C1, C2, C3 and K. So, 4 parameters to represent this muscle force. So, these 4 parameters C1, C2, C3 and K can be obtained from the experiments by performing actual experiments. So, one can find these muscle parameters. So, now, so if you see this equation of motion can be written mu double dot plus Ku plus U dot plus F muscle equal to F sin omega t, or it can be written by substituting this value of F muscle and dividing this m, it can be written U double dot plus K by m plus C1 plus C2P plus C3P square by m L max into U plus C by m U dot plus K by m U cube equal to F by m sin omega t. So, U is the displacement. So, here you can see, so the coefficient of U can be taken as the natural frequency of the system. So, here omega 0, the constant. So, this is a constant part. So, here you can take this as a constant part. Sometimes we can take this p to be a function of so p can be varying with time. So, in that case it cannot be constant. So, this constant part coefficient of u can be taken as this omega 0 square. So, that is why this omega 0 equal to root over k by m plus C 1 plus C 2 p plus C 3 p square by m L max. So, you can notice that this natural frequency of the system we can vary by changing this muscle pressure. So, by changing this pressure P, so we can actively control the frequency of oscillation. So, as you know, by controlling this frequency of, so this natural frequency we can always avoid the resonance frequency, or the resonance frequency can be away from the natural frequency, so that the resonance condition can be avoided. Or whenever we required, we can control this muscle pressure and we can bring it to the resonance condition, so that we can have maximum displacement. So, in this artificial muscle case we require the displacement to be more. So, as we require the displacement to be more, so that it can take more load or it can displace it more. So, in that case we have to operate near the resonance condition. So, we have to change this value of omega 0 by actively changing this pressure which we can supply from outside, and we can control the motion of the system. So, the non-dimensional displacement x we can take now, this thing we can modify and we can take this x equal to u by r. So, is used as a spelling. So, here r is used as a scaling factor. So, a non-dimensional time tau also can be taken as omega 0 t. So, by taking this non-dimensional time omega 0 t, so we can write down this equation motion in a more simplified form. That is why this non-dimensional time is used. Also one can use this bookkeeping parameter. So, epsilon, so which is very less than 1 to write down this equation of motion in a better form, where we can apply this perturbation method to solve this equation. So, here we are taking this omega equal to omega by omega 0. So, this omega is the external frequency and omega 0 is the natural frequency we have taken. So, mu we have taken equal to c by 2 epsilon m omega 0, and alpha equal to r square k by epsilon m omega 0 square, f equal to small f equal to f by r epsilon m omega square. So, writing this way, so you just see the equation now is converted to a better form which is well known to you. So, which is similar to that of a doping equation. So, this is d square x by d tau square plus 2 epsilon mu dx by d tau plus x plus epsilon alpha x q equal to epsilon f sin omega t. So, you just see, so we have make the system in such way that the forcing is weak nonlinearity, forcing is of weak nonlinearity, epsilon f we have taken. So, if the forcing is very high, then in that case this epsilon term will not be there. So, it can be f sin omega t. So, in that case the excitation will be hard excitation. So, here we are taking this cubic nonlinear thing. So, cubic nonlinear stiffness we have taken. So, that is why this is epsilon alpha x q, and the damping, viscous damping we have taken, and the viscous damping we are considering it is of epsilon order. And after writing down this equation of motion, so we can apply. So, there are several methods to solve this equation of motion, So, the system is considered to be harmonically excited, which undergoes simple resonance condition at omega equal to omega nearly equal to 1. So, here you just see the coefficient of x equal to 1, that is the natural frequency. So, as we have written it in non-dimensional form, the non-dimensional natural frequency is 1. That is why this non-dimensional external frequency, whenever it is nearly equal to 1, so we have the resonance condition. and this resonance condition is the simple resonance condition. So, by using second order method of multiple scale, the reduced equation can be written as, so it can be written, so dA by dt equal to epsilon into minus f by 2 cos gamma minus mu a plus epsilon square 1 plus 2 mu by 2 into f by 2 sin gamma minus 3 by 8 alpha a cube, and a d gamma by dt equal to a epsilon sigma minus epsilon into minus f by 2 sin gamma plus 3 by 8 alpha a cube plus epsilon square 1 plus 2 mu by 2 into minus f by 2 cos gamma minus mu a plus epsilon square 3 alpha square a to the power 5 by 256. So, as you know, for steady state a and gamma will not be function of t. So, the left hand side will be equal to 0. So, now we can have a closed form solution and we can solve that closed form solution to find the response of the system. So, here these are the, so by performing experiments actually we got these parameters C1, C2, C3, alpha, mu, taking this L max equal to 74 mm. So, all these parameters have been obtained. So, other parameters what are taken are here. So, by taking all these parameters, so it is modeled and you can see the response. So, initially there is a comparison between the response obtained from this method of multiple scale and by solving this original equation using this Runge-Kutta method. So, you can see, so there is a, so it is closely matching. So, both the, so this is numerical solution and this thing is closely matching. So, from the time response and the phase portrait you can see this method of multiple scale is giving a close response. So, the advantage of using this method of multiple scale is that, so now we can plot the frequency response plot. So, this is the frequency response plot. So, in this numerical way, so if you are going to use this Runge-Kutta method to solve or to find this frequency response plot, you just see. So, you have to solve that equation for here, for example, we have taken more than 1000 points. So, at 1000 value of sigma you have to solve that equation using this Runge-Kutta method, and there you required a huge memory space to store those 1000 data, and from those data again you have to find the steady state value of A to plot this response. So, but by using this closed form solution what we have obtained, so you can find this frequency response with a fraction of second, but you may require huge computational time. So, if you are using this Runge-Kutta method to find this frequency response. Okay, so here again you just see, so this is a stable branch and this is unstable branch, and here we have a saddle node bifurcation, or here rather we can have a hop bifurcation, and here we have a saddle node bifurcation. So, at this point, so if we are reducing the frequency, so you can see the system can jump from here to here. So, it can jump from here to that point. So, if we are taking 2 points, so you just see here at M, so we have only one response, but if we are taking a point at N, so you can see, so we have 3 response are there. So, 2 stable and 1 unstable response is there. So, to get to which stable or unstable response the system is moving, so we have to plot the basin of attraction. So, the basin of attraction is plotted here. So, at M1 you can see that M point what you have shown. So, you have only one response. So, here A can be found less than 0.1. So, that thing clearly you can visualize here. So, this is the A value you are getting at the frequency at a sigma. So, at a sigma correspond to M1 M, and the other point. So, you can see we are getting, so this correspond to the saddle node point, and these correspond to. So, here clearly you can see, so we have two stable response. So, all the branches or all the trajectories are moving to this point. Here also all the trajectories from this basin. So, you just see from this basin all the trajectories are moving here. Here also from all the trajectories they are moving to this point. So, if you are taking some initial condition from here, so it will traverse to or travel to this point, and if you are taking some initial condition here, so you will get this stable response. And here, so this actually this unstable point cannot be achieved with time. So, it will take infinite time to reach this saddle node bifurcation point, as this is unstable point. So, either the response will go to this point or this point. So, this way you can find the basin of attraction. So, for different system parameter, these things have been studied, frequency response variation with the different system parameter. For example, so in this case we have taken two value of mu, that is damping. So, with damping it is reduced, you can see. Then with different pressure, so 100 kPa and 1000 kPa. So, by applying this higher pressure, you just see, so this is the response plot, and for the lower response, so inside plot is for 100 kPa and outside plot is for higher kPa, that is this kilo Pascal pressure is applied here. So, then muscle parameter C1, C2. So, these are the muscle parameter. For different muscle parameter, you know that the muscle parameter depends on the materials we are using. So, by using different materials, so they can be changed. So, having different muscle parameter C1, C2, then this is C3, and this is the nonlinearity, effect of nonlinearity you can see. So, this is alpha equal to 75. So, this is alpha equal to 300. So, then these are the forcing amplitude of forcing 1 kilonewton, 3 kilonewton. So, due to higher forcing the response amplitude is high, and due to, so then this variation of K is also taken, this nonlinear term in this muscle force. So, due to that thing also it has been plotted. So, you can find, so this way you can find the different response, and also you can apply it for a different application purpose. So, here we are not going to tell you in detail regarding this application purpose. So, this is a machine developed to study the harmonically excited palm. So, this is the spring is connected here. So, this is the artificial muscle, and this is the controller through which we can give the air pressure to the system. So, by taking this air pressure, so it is here, it is intended to rotate this or move this arm. So, some load we have put here. So, you can see arm with load. So, here we have a rack and pinion system. So, when this pulley is moving, so it can move this rack and pinion. So, in turn, so it is connected to this arm and it will rotate this link. So, this is particularly can be simulated or it can be mimicked. It can mimic the motion of the arm. So, by putting this artificial muscle, so for paralytic or semi paralytic person, so we can move this arm. So, effectively we can use this muscle for the purpose of exoskeletal systems also. So, you can see this is the so to characterize these things. So, we have put the load, and by giving different air pressure, so we have seen so how much load it can take. So, single muscle, so we can have different muscles also. So, these are the vibration of the muscles. So, experimentally it is validated that it is giving this correct result. So, you can, so previously we have seen that thing as a force excited. So, now we can consider this as a parametrically excited when we consider this P to be a function, time varying function of time varying function. So, here we can take this P, similar way we can analyze the system, and here that P part we are taking it equal to P0 plus P1 cos omega t. P can be taken as Pm plus P0 sin omega t. So, here P is taken to be Pm, previous case we have taken P equal to P only, but here now we are adding a term that is P0 sin omega t in this pressure. So, in that case the same equation we are taking, that is F muscle equal to U p, that is U1 plus E2 p plus E3 p square into U by L plus D1 plus D2 p. So, here we have taken a 5 parameter C1, C2, C3 3 parameter and D1, D2 another 2 parameters. So, 5 parameter muscle parameter we have taken. So, this part is a function of U and this is independent of U. So, that is why we have taken 2 parts. So, now you can observe this equation can be written as that of a parametrically excited system. So, you just see this is U double dot. So, this part is a constant part in U. So, we will see. Okay. So, now this is the equation. So, simplified equation d square x by d tau square plus 2 epsilon mu dx by d tau plus epsilon into 1 plus P1 sin omega t plus P2 cos 2 omega t into x. So, you just see the coefficient of x. So, this part, so 1 into x, that is the constant part, but this other 2, that is P1 sin omega t and P2 cos 2 omega t, when they are coefficient of x. So, this leads to parametric excitation, and in the right hand side also we have the forcing, that is a constant part is that epsilon f1 plus epsilon f2 sin omega t. So, here, so we can have different resonance conditions. So, by applying this method of multiple scales, so we can study different resonance conditions. So, we can have this principal parametric resonance condition when omega nearly equal to 2, and so in case of principal parametric resonance conditions, again this numerical and analytical responses have been plotted. So, here you can see these parametric instability regions we have found. So, S is the region for where the system will be stable, that means the muscle will not contract in this region where S is written. So, we have to operate the muscle in a region where it is U, it is written U, so that there will be some contraction in this muscle. So, if it is in the region S, so it will not contract, and when it is region U, so it will contract. So, by using this parametric instability region, so we can study different response of the system. So, these are the instability region for different purposes, one can study this thing. Okay, so this is for principal parametric resonance, some comparisons have been here. Okay. So, this is principal parametric resonance, trivial state instability regions have been plotted and these verifications have been carried out. Similarly, this experimental verification have been carried out. So, this is this experiment, this muscle force versus the contraction U. You have seen the experiments we have performed where we got different muscle force versus the contraction. So, for different pressure, so these things have been plotted. So, this for example, this is 50 kPa, this is 100 kPa, this is 150 kPa. So, this is the muscle force. So, taking these things, so we can obtain the C1, C2, C3, D1, D2 from this experimental value, and so initially we can put a linear curve to find the slope of that curve, and from that thing, so we can get some parameter C, C1, C2, and then from this linear curve fit we can put the linear curve fit and we can get the muscle parameter. So, taking those muscle parameters, So, it has been also verified that the experimental and theoretical values are coming to be similar. So, one can study combined response also. So previous case we have not taken this nonlinearity, here one can take the nonlinearity also. By taking the nonlinear system, again different resonance conditions can be studied. So, one can study the principal parametric resonance conditions omega nearly equal to 2, then simultaneous resonance conditions where omega equal to 1, and so these responses can be obtained. And so, for different application purpose one can study these responses. Here clearly one can draw the basin of attraction to study the when there is multiple solutions. So, these basin of attractions can be plotted to get the physical realization. So, for what initial condition the system will have this response. So, clearly you can see, so this is the saddle node point, this is also a saddle node point. So, these are the stable points. So, it is coming to these stable points. So, here also you can see this basin of attraction. So, this way, so you can study different pneumatic artificial muscle for different application purpose, and you may model this as a force excited or direct excited or parametrically excited system. So, next class we are going to study some other systems, particularly where we will discuss regarding the chaotic response and how to control the chaos in different systems. So, thank you very much.